Good afternoon, everyone. So we'll start the session now. Let others join in the meantime, if because we will be giving introduction only in the first 5 minutes anyway. So I welcome you all for the problem solving session for this NPTEL course, Computational Fluid Dynamics, and the course code is given over here, NOC 25CH18, and this is our fourth session. We are into fourth week for the problem solving, and the session is from 3 p.m. to 5 p.m. It like we have been meeting for the past 3 weeks, and from 3 p.m. to 5 p.m. every Saturday. So this will continue unless and until if any changes are there, it will be informed prior through email only. So yeah. So the course instructor is Professor Sreenivas Jayanti sir from the Department of Chemical Engineering, IIT Madras, and myself, TA Karthika. So I am a research scholar from Department of Chemical Engineering, IIT Hyderabad. So this particular course, that is the Computational Fluid Dynamics, is a 12 weeks course where it is covering everything from the basics to the advanced things. Like it is covering from finite difference approach and moving towards the finite volume approach, and also at the end you are having a introduction to the turbulence models as well. So the course layout is as follows. So in the first 2 weeks of the class, you have learnt about calculation of flow in a rectangular duct and the triangular duct, so that it gave you an idea of the finite difference approach and the finite volume approach, which is like what we are implementing in CFD. And second week it is about calculation of fully developed flow in a triangular duct, as you mentioned. And third week it is about derivation of equations governing fluid flow. So CFD is nothing but wherein you solve the problem in the hand. So how do we go about solving the problem? So we are just solving the equations. So that equations are nothing but which define the fluid flow. So for example, if there is a only cold flow in the system, that is there is no exchange of heat or exchange of mass in the system. Mass in the sense there is no external reaction happening inside the system. So we have only continuity equation and momentum conservation equations in the XYZ directions. So first we define the system, that is we define the geometry of the system, and later we divide the system into smaller grids, and in each of those grids we solve the equations and we get the fields like velocity fields, and if it is temperature is involved, we get temperature values. So in each of these grids we get the velocity, temperature, those things. And the approach which we use to get the grids and further calculation will be like finite difference approach, finite volume approach, or finite element approach. So these things only you will covering, and for that, and to get to know that, you need to know what are the equations involved in the system, and later how to go about solving. Most of the equations are partial differential equations, so you must be aware of the numerical techniques which we use to solve those equations to get the final results. So in week 4 it is about equations for incompressible flow and boundary conditions, wherein typically like we have parabolic, elliptical, and hyperbolic conditions. And also in this week we have seen about energy transfer equations, energy conservation equations, and it is about heat transfer problems, and also mass transfer aspects were also seen, like what will happen if there is like equation mass transfer through reactions which is happening, and what are all the equations that will be involved, and also mass transfer chemical reactions. So those excuse me, those particular things we have seen. And at last it is about the well posedness of numerical solutions, numerical problems. So in order to get the solution, the problems should be well defined, and it should have a unique solution. So only then we can proceed with getting the solutions. Otherwise, there is no point in solving such systems also. So those things and all we will be we have seen in the lecture of week 4 from the professor. So similar problems associated with the similar concepts we will be seeing in week 4, and week 5 it is about basic concepts of CFD like finite difference approximations, and week 6 it is about again I told right, like consistency, stability, convergence. Those things we must keep in mind to get a proper solutions. Otherwise, CFD if we are not very careful about these things, right, we will get solutions but they won't be following the physics behind the system. Like we will be getting some answers, some results, but it would be like entirely wrong. So those things we should be aware of. And later on it will be about solution of Navier-Stokes equations for compressible flows and incompressible flows. And at last it is solution of linear algebraic equations, basic methods and advanced methods. As I mentioned, what we do is that through these discretizations, we convert the partial differential equations into the linear algebraic forms, and later on we must have numerical techniques to convert it from the to get the solution uh, by using certain numerical techniques. Like for that we will be having a basic methods and advanced methods which will be covered. And lastly it is about basics of finite volume method including grid generation. Like there are many aspects. If it is a rectangular circuit which you are dealing with, it will be easier to divide it into smaller grids. You can get a coarser or finer mesh depending on your requirement. You can get, if it is a simpler system like a rectangular grids or even a circular pipe, but that won't always be the case. For example, if any complex system you are having in hand and you need to divide it properly, so there are so many techniques like structured grid, unstructured grid. Like it won't follow certain patterns, and but if there is a structured grid, ease of solution will be there, but otherwise it will be difficult. So all those things you will be seeing in week 11. And last it is about turbulence flows and turbulence modeling. So this is the course layout for the 12 weeks, and now we are in equations for incompressible flows. And so in this week problems we will be discussing on um, heat transfer, mass transfer, and also involving chemical reactions, and also like boundary conditions, and those things we will be dealing with when we are dealing with the problems. So for the books and references, we have Verziger and Perrick computational methods so for fluid dynamics, and second here's numerical computation of internal and external flows, and Patankar SV numerical heat transfer and fluid flow, and Verstig and Malal Sekara an introduction to computational fluid dynamics, the finite volume method. And last it is Anderson JD computational fluid dynamics, the basics with application. So now we will go to this week's problems. So we have actually like 20 problems or so, and we have two cases. Depending on those cases, the problems that are following we need to answer. So first, before that, let us just understand what are all the governing equations in the fluid flow systems, so that when we are dealing with problem, we can directly apply this equations that time. So just to give you an idea. So basically, like we have four things happening inside any systems. Like one is like continuity equations and the momentum transfer equations we use, and the next one is we have if energy by heat transfer is taking place inside the system, we need to account yeah, conservation of energy equations as well, and species balance equation as well. If reactions are happening, we need to account for the conservation of species inside the system as well. So first one is continuity equation, and it is all these equations are in the vector form, so we haven't split into x, y, z or those terms, those splits we haven't made. So in this particular slide, whatever the equations are, those equations are in the vector form. So the continuity equation is that it is given by dou rho by dou t plus del dot rho u equal to 0. So it is like conservation of mass, and the first term what it specifies is that it is the change of with respect to time, and the second one is the convective term, that is it associates with the change due to the flow. And so in this is the continuity equations, and we just account it like mass transfer, mass is conserved in the system. And the second one is the momentum conservation equation, and it is given by dou u by dou t plus del dot u equal to nu, that is mu by rho into del dot del u plus g minus 1 by rho into delta p. So momentum conservation equation just stems from the Newton's second law of motion, that is F is equal to ma. So m into dv by dt, so that all the forces conserved inside the system. So it is just a force balance equation. So again this term dou u by dou t plus del dot u into u. So this is again change with rate of change with respect to time, and this is like convective change due to the convective motion, and I mean convective term. So equal to all the forces acting inside the system. So first one is like this is the viscous force. So it is like momentum change due to the diffusion, and this is G, that is gravitational force, or we can say body force. So it is from the body force, and it is minus 1 by rho into delta P, pressure gradient force. So all these force like F is equal to ma, so that is the concept. So momentum change due to rate of change with respect to time, and momentum change due to the convection, and it is like momentum change due to diffusion and plus body force, and it is the effect due to pressure gradients. So that is the momentum conservation equation. And next comes the energy conservation equation. So for that we have dou t by dou t plus del dot dou t by dou t plus del dot u into t equal to k by rho cp into del dot del t plus mu by rho cp into phi v plus qr by rho cp. Again here it is rate of change of temperature with respect to time, and it is like change due to the convective term, and equal to k by rho cp. So here k denotes the thermal conductivity, and Cp is the that change of mass per unit time per unit kg, and del dot delta T plus mu by rho Cp into phi v. Phi v is nothing but it is the viscous dissipation term, and it is often neglected in heat transfer problem. So, so we'll see that why in one of the problems we'll see plus QR by rho Cp. So QR is the rate of reaction. So that term also, like we'll see the significance in the next slide. So dou t by dou t plus del dot u into t equal to k by rho Cp into del dot delta t plus mu by rho Cp into phi v plus QR by rho Cp. So here K is thermal conductivity and Cp is specific heat capacity at constant pressure, and mu is like viscosity and rho is density, and phi v is the viscous dissipation term, and Qr is the rate of reaction, I mean heat produced with that. So we'll see that. So this is for energy conservation. And for species conservation, again we have dou into rho yi by dou t plus del dot rho into u into yi equal to del dot gamma delta yi plus SI. So Y is the species fraction or species mass, and SI is the source term. So these new terms, what it means with respect to reaction, we'll see in the next slide. So we in general we have continuity equation, momentum conservation equation, energy conservation equation, and species conservation equation. So the species conservation equation comes into picture when we are dealing with new reactions. Thereby reactants get used and new products gets formed. So for example, consider this reaction, AR1J into X1 plus AR2J into X2. It is reacting to give some products like AP into YI, AP2 into Y2, something like that. So generalized equation, some reaction is happening wherein reactants are utilized and products are getting formed. And here the source term is, which we saw in species conservation equations, is coming something like Wi into summation over J is equal to 1 into Nr APIJ minus ARIJ into RJ. RJ is the rate of the reaction, and QR is again like which comes in the heat transfer energy conservation equation. So again it is the summation of J equal to 1 to Nr Rj into Ji is equal to 1 into Ns AP. Some it will be like this, where delta HF is the heat of formation or heat of that, those concepts which we give. So from that only QR is coming into picture, that is heat of reaction. So next is like we are giving IRJ. So how it is used, it is like KFI, and into it is given over something like this: I equal to 1 to Ns Xi into Aij minus Kbj into I equal to 1 to Ns Xi into Wij, something. So reaction rate constants are expressed in terms of Arrhenius coefficients, in terms of activation energy and temperature exponent and pre-exponential factor. So all these terms are used in expressing the reaction rates. So explicitly these terms are not present in the that is reaction rate terms are not present in the heat transfer and the mass transfer equations. I mean heat transfer, okay, mass transfer, I mean species conservation equation. But inside species we are able to see the presence of these terms. So chemical reactions, so this is the case. So KFI, that is like KFI equal to AF into T into beta Fi exponential of minus EFI by RT. That is the Arrhenius coefficient is expressed in terms of activation energy, temperature, exponent, and a pre-exponential factor. So all these things are coming. So now we'll move on to the problems. So we have two cases. The first case is this one. So we need to solve for the flow in a reactor in which carbon monoxide is getting converted to carbon dioxide with the production of hydrogen on a catalyst. So it is a water gas shift reaction, and carbon monoxide plus water giving carbon dioxide plus hydrogen over a catalyst. Let us assume a simple configuration for this reactor. See figure. The multigas mixture flows through a rectangular channel. Due to its reaction, its composition changes from inlet to outlet. The top and bottom of the walls are coated with the catalyst, and two side walls are used to heat up the gas to the desired temperature of 200 degrees Celsius. For the given flow rate of air with the given concentration of four gases, for given side wall heat flux and given catalyst surface area, we wish to calculate the percentage conversion of carbon monoxide to carbon dioxide by the time it reaches the end of the channel length. We want to find this out using CFD simulation. Assuming steady laminar flow and first order reaction kinetics for the reaction, answer the following questions. So what is happening? We are just solving for the flow in a reactor wherein carbon monoxide is getting converted into carbon dioxide and hydrogen is getting produced by using this particular by using this particular reaction over a catalyst. So we'll see the figure first. So it is a simple figure where it is like a rectangular channel or rectangular bed. So let us assume a simple configuration for this reactor. So R okay, is like this rectangular channel. Oh, hmm. Let us just assume this as the rectangular reactor. So the multi-gas mixture flows through the rectangular channel. Due to its reaction, its composition changes from the inlet to the outlet. So let us consider this as our inlet and this is as our outlet. So its composition changes from inlet to outlet. Top and bottom wall are coated with catalyst. So the bottom wall, so this top wall and bottom wall is coated with catalyst, and the side walls are used to heat the gas to the desired temperature. So by some means the side walls, both the side walls are used as a heating to 200 degrees Celsius. So what is given from inlet to outlet, its composition is changing, and top and bottom walls are coated with the catalyst, and two side walls are heating used to heat the gas to the desired temperature of 200 degrees Celsius. So for this particular flow rate with the concentration given for the four gases, for given side wall heat flux and given catalyst surface area. So what is given? Flow rate of air is given and concentration of four gases and also heat flux is given. Catalyst surface area is given. We are asked, not we, it is desired to get the percentage of conversion from carbon monoxide to carbon dioxide by the time it reaches the end of the channel. So from inlet to outlet, if we know the flow rate of air and concentration of four gases for given side heat wall flux, because we are heating it to 200 degrees Celsius and catalyst surface area is given. So we are asked, it is desired to find the conversion percentage of carbon monoxide getting converted to carbon dioxide by the time it reaches the outlet. So we want to find this out using safety simulations. So this is the concept. Now we will go and see the questions that is coming out of this problem. So first is that, and this is the case figure. So first question we'll see. First one, which of the following needs to be specified for statements is true about chemical reaction? Which of the following needs to be specified for statements is true about chemical reaction? We'll see the statements first. Okay, which of the following needs to be specified for statements about chemical reaction? First one is rate of reaction, second one is reaction kinetics, and third one is heat of reaction. Option A 1 only, option B 2 only, option C 1 and 3, option D 2 and 3. So when we are dealing with chemical reaction using the CFD problem, what are all the things needs to be specified? So first one, it is given as rate of reaction, second one reaction kinetics, and third one heat of reaction. So first we'll go through step by step. So rate of reaction, it is like a varying with respect to time, position, everything, and it gets calculated if we know the certain reaction kinetics parameters. So we need not specify the rate of reaction because first we do not know, and second it will vary with that particular time or particular location or particular position or whatever. So rate of reactions we need not be specifying. Second one, reaction kinetics we need to specify, and because only then we can know about the conversion, those things we can know from the reaction kinetics. So in reaction kinetics it will like include certain things like stoichiometric coefficients and those things. And third one is heat of reaction. Again we need to know the heat of reactions. Because if you remember in the energy conservation equation, heat of reaction term comes into the picture. Like not directly, but QR term comes, and from the QR term comes. So it is calculated based on the heat of formation of the products, formation of the reactant, consumption of the reactants, those things. So reaction kinetics and heat of reaction needs to be specified. So right answer is 2 and 3. So that is given from option D. Option D, 2 and 3 is the right answer. So answer is option D. So now coming to question, okay, it is like kinetics of the reaction, meaning stoichiometric coefficients, order of reactions, and rate constants in the rate equations, if any, needs to be known. So question 2 it is, which of the following do we need to specify about the catalytic reaction? First one is activation energy, second one is catalyst surface area, and third one is order of reaction, fourth one is reaction mechanism. So when we are following, which of the following we need to specify when we are dealing with the catalytic reaction? First one is like activation energies. We need to specify the activation energy. And second is the catalyst surface area. Again, this we need to specify. Third, order of the reactions. This is we need to give, because only then we can get to know the conversion, those things and all. And fourth, it is reaction mechanism. We need not specify the reaction mechanism. Like given thing it can do on its reaction mechanism is not required. So which of the following do we need to specify about the catalytic reaction? Is that 1 is true, 2 is also true, 3 is true, and 4th is false. So option A, it is 1 only. Option B, it is 1 and 2. Option C, 1, 2 and 3. Option D, 1, 2, 3 and 4. So option C is the right answer, 1, 2 and 3. Activation energy, catalyst surface area, order of the reaction. So option C is the right answer. Now moving to question 3. In question 3, we have how many mass conservation equations do we need to solve? So first one, it is option A, only 1. Option B, 2. Option C, 3. Option D, 4. So we need to know how many mass conservation equations we are solving. So if we go back and look at the equations, we have one continuity equation and three, what do we call, a momentum conservation equations, and temperature and energy conservation equation, and at last species conservation equation. So we are using, if we talk about mass conservation equation, we have continuity equation and species conservation equations. So species conservation equations, we will write it for all the species. So we have how many species? Carbon monoxide, carbon dioxide, hydrogen and water. We have 4 species and one overall continuity equations. So but by using the degree of freedom, if we solve for the continuity equations, if we solve for if total number of species is ns, consider it as ns. If we solve for ns minus one number of species conservation equation, it is sufficient. So ns minus 1 species conservation equation plus 1 continuity equation, so it will be total ns number of mass conservation equations we need to solve. So ns here is that carbon dioxide, hydrogen in the products, and carbon monoxide and water in the reactants. So we have 4 species. So answer is 4 actually. How many mass conservation equations do we need to solve? Answer is 4. Option D, 4 is the right answer. So yeah, number of species is 4. Carbon monoxide, hydrogen, carbon dioxide, water, and continuity equation we have 1, and species conservation equation equal to ns minus 1. As I mentioned, it is 4 minus 1, so it is 3. So total number of equation is equal to ns minus 1 plus 1 equal to ns. So it is ns here in this particular context is 4. So answer is 4. Now we will go to question 4 actually. In question 4 it is asked that assuming the flow to be three-dimensional, total number of partial differential equation that needs to be solved is dash dash. I repeat, assuming the flow to be three-dimensional, total number of partial differential equations that needs to be solved is dash. So we have a three-dimensional system, and based on that, how many partial differential equations we need to solve? Option A 5, option B 6, option C 7, option D it is 8. So option A 5, option B 6, option C 7, option D 8. So what is being asked in the question is that we are assuming the flow to be a three-dimensional flow. So it is a flow through a rectangular channel. So we are taking into consideration all three dimensions. So if that is the case, how many partial differential equations do we need to solve? So answer is option D, that is option D 8 is the answer. Why? Because to be more precise, how it is, we have one continuity equation and three species balance equation that we have seen in the last problem itself. So we have four mass conservation equation. Similarly, we have three momentum conservation equation and one uh, energy conservation equation. So 3 plus 1 again 4 equations. So total number of partial differential equation becomes 4 plus 4 8. So option D 8 is the right answer. Answer is option D, that is 8. So continuity equation 1, mass conservation equation 3, and energy conservation equation it is 1. Species conservation equation it is 4. Actually it is 4, but since we are already solving for the continuity equation, it becomes 4 minus 1, that is ns minus 1, so 3. So on the whole it is 1 plus 3 plus 1 plus 3, it is 8. So total is equal to 8. So 8 equations, that is 8 partial differential equations need to be solved in this system. Assuming the flow to be three-dimensional, we have 8 partial differential equations that needs to be solved. So now moving on to second case. So this is second case. Choose the correct answer from the options given below. We need to design a reactor in which the following steam reforming of methane is being done to produce hydrogen as per the following reaction. So we are asked to choose from the options below. For that, first the case is such a way that we are asked to design a reactor, and what reaction is being happening is that it is a steam reforming of methane and end product is hydrogen. So the reaction is that methane plus water plus 206 kilojoule per mole of heat gives carbon monoxide plus hydrogen. So methane plus water plus this amount of heat giving carbon monoxide plus hydrogen. Carbon monoxide giving hydrogen. So what is given is that reaction is endothermic and is to be carried out at a higher temperatures, 800 degrees Celsius, based on the desired output composition. All the species are in gas phase, but the reaction is catalytic. Reactants will have to diffuse to the catalyst, which is coated on the bottom wall of the reactor, see figure, between planes B and C, which are at a distance of 0.5 times length and 0.75 times length respectively. Reactants are heated to the desired temperature by heating the gas mixture over the length of the transverse between the planes A and B. Further, heating needs to be between planes B and C to provide thermal energy for the endothermic reaction. For a given reactor of length L, height H and width W, flow rate and composition at the inlet and thermal wall boundary conditions on the bottom wall, we need to find out how much conversion takes place. That is, how much of methane coming through the inlet gets converted to hydrogen. We want to find this out using CFD simulation. Assuming steady laminar flow, answer the following questions. So this is the problem statement. So first we'll look at the figure and then come back to the question. So this is like a rectangular plane and it is A, B, C and D. So between B and C only catalyst is coated, and between A and B heating is done. So a catalytic reactor flow having dimensions W, H, L in the XYZ, in the along the Z direction it is L, and it is width and height in the Y direction, right? Width W, H, L in the XYZ direction, such that, so where is this? This is W and this is H and this is length, such that W is very much greater than H and L is very much greater than W. Gaseous mixture of carbon monoxide and water enters the reactor through plane A and leaves through plane D. Catalyst is coated on the bottom wall between planes B and C, which are at a distance of 0.5 times L and 0.75 times L from the inlet. It is midpoint 0.5. If it is 1 meter, it is 0.5 meter, and plane C is at a 0.75 times length along 3/4 from the entrance. Reactor is preheated through the top and bottom walls over planes A and D, A and B. So here heating is done and here reaction is being done. Is it visible? Okay, here reaction is being done. So I repeat, catalytic flow reactor having dimensions W into H into L in the XYZ direction, such that length is very much greater than W and W is very much greater than H. Gaseous mixture of CO and H2O enters the reactor through plane A and leaves through plane D. So catalyst is coated on the bottom wall between plane and C. Between planes B and C, catalyst is coated on the bottom wall, and B plane is at the exact midpoint between planes inlet and outlet plane, and plane C it almost along 3/4 length of the total length, at a distance of 3/4 of the total distance from the inlet, and we are preheating the reactor through the top and the bottom walls between distance A and B. Between planes A and B, heating is done, and between planes B and C, planes are coated with the catalyst surface, so we can have the reaction. So now we'll go back and look at the question once again. We need to design a reactor in which following steam reforming of methane is being done to produce hydrogen as per the following reaction. Methane plus water is giving carbon monoxide plus hydrogen. So it is an endothermic reaction and we are supplying heat, that is very high temperature, 800 degrees Celsius, for us to get desired output composition. All species are in the gas phase, like methane and steam are in the gas phase, and B and reaction is a catalytic reaction, and so reactants have to diffuse to the catalyst which is coated on the bottom wall of the reactor. Between planes B and C, we have seen the catalyst coating at the bottom wall. So reactants will have to diffuse through the catalyst to get the diffuse to the catalyst, which is at the bottom of the planes between the planes B and C. So planes B and C are at a distance of 0.5 times L and 0.75 times L. So we are also preheating the reactants to the desired temperature over the length of the traverse between the planes A and B. Between planes A and B, as the reactant mixture is moving, we are heating them to a desired temperature, and further heating needs to be done between planes B and C to provide thermal energy for the endothermic reaction. Again, between planes B and C also further heating needs to be done, because it is an endothermic reaction. We are supplying external heat to the reactor. For a given reactor of length L, height H and width W, flow rate and composition at the inlet and thermal wall boundary condition on the bottom wall, we need to find out how much conversion takes place. So length, height, W measurements are known, and flow rate of the reactant mixture and composition of the reactant mixture at the inlet is known, and thermal wall boundary conditions on the bottom wall, we need to find out how much conversion takes place, how much of the methane coming through the inlet gets converted to hydrogen. We want to find this out using safety simulations, and we are assuming steady laminar flow conditions. So I hope it is clear now. This is actually methane, not CO. Gaseous mixture of methane and water enters through reactor plane and leaves through plane D. Alright, now we will go to questions. So the first question is that how many mass conservation equations do we need to solve? How many mass conservation equations do we need to solve? It is similar to the last case that we have seen. So options we will see, but without options also we can say that it will be like, again we have 4 species, that is methane, carbon monoxide, steam and hydrogen. So 4 species and 1 continuity equation. So total number of mass conservation equations we need to solve will be 4. So but we will look at the options once. Option A, only the one for methane. Option B, only for hydrogen. Option C, only those for methane and steam. And option D, we need to solve 4 mass conservation equations. So option D is the right answer, because we need to solve the mass conservation equations, that is species balance equations, for the methane, hydrogen and steam, and also like total, like one more thing is carbon monoxide. It can be like any 3 of these species and 1 continuity equations. So on the whole we need to solve for 4 mass conservation equations. So answer to this question is option D is the right answer. We need to solve 4 mass conservation equation. Option D is the right answer. And now we will move on to question 2. In question 2, what is asked is that in order to model the effect of reactant concentrations on the chemical reaction rate correctly, which of the following needs to be specified? I repeat the question. In order to model the effect of reactant concentration on the chemical reaction rate correctly, which of the following needs to be specified? So, chemical reaction is happening, and to model the effect of the reactant concentration, which of the following needs to be specified? So, first we look at that. Option 1, reaction rate constant. Option 2, reaction rate. Option 3, equilibrium constant. So options are option A 1 only, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. So in this question we are asked to find which of the factors actually needs to be specified for us to model the effect of reactant concentration on the reaction rates, on the chemical reaction that is taking place inside the system. So first one is reaction rate constant. So we know now that we need to specify the reaction rate constant. So option 1 is true. Second one, reaction rate. Reaction rate is like depending on time and position, it varies. So we need not specify that actually. So 2 is wrong, and similarly equilibrium constant we need not specify. So the right answer is option 1, that is reaction rate constant. So from the given options of A, B, C and D, only in option A 1 only is given. So option A 1 only is the right answer. So now we will go to answer is option A 1 only is the right answer. Now we will go to question 3. In question 3, okay. In figure, which of the following statements is true in the section AB, assuming that a constant wall heat flux is imposed? So if you remember the picture, AB is the zone where we are preheating the reactants. So which of the following statements is true in the section AB, assuming a constant wall heat flux is imposed? So we look at the statements first. First one, cross-section averaged gas velocity remains constant. Second one, gas temperature will increase linearly. Third one, concentration of methane will decrease monotonically. So first one, it is like cross-section averaged gas velocity remains constant. We cannot comment on it because it is A and B is the initial zone where we are preheating the reactants. So it is like cross-section averaged gas velocity remains constant, we cannot say. Second one, gas temperature will increase linearly. So in the A and B zone, between the planes A and B, where we are preheating the reactants, we can say that the gas temperature will increase linearly because we are heating the reactants. We want the reactants to be at a higher temperature, so 800 degrees Celsius approximately. So from the inlet to the B section, we are heating the reactants. So obviously the gas temperature will increase linearly. Third one, concentration of methane will decrease monotonically. If the reaction is happening, concentration we can talk about how it is affecting. But between planes A and B, there is no catalyst sitting on the planes. Only between planes B and C, catalyst presence is observed. So methane concentration will not decrease in the first plane and first zone, that is between planes A and B. So concentration of methane will decrease monotonically is also false. So we look at the options first. Option A 1 only, option B 2 only, option C 1 and 2, option D 1 and 3. So as I mentioned, only second statement is right, that is gas temperature will increase linearly. So that is the only correct statement. Why gas temperature will increase linearly? Because we are externally heating the planes between A and B, And also it is mentioned that constant wall heat flux is imposed. So the gradient is constant, so the increase will be linear. So answer is option B. 2 only is the right answer. Option B, 2 only is the right answer. Once we will go and read the statement correctly so that it would be more clear. The reaction is endothermic and is carried out at a higher temperatures based on the desired output composition. All species are in gas phase, but reaction is catalytic. Reactants will have to diffuse to the catalyst, which is coated on the bottom wall of the reactor between planes B and C. So between planes B and C only catalyst is coated, and reactants are heated to the desired temperature by heating the gas mixture over the length of traverse between planes A and B. Further heating needs to be done between planes B and C to provide thermal energy. So that is the thing. So even if we look at here, it is gaseous mixture enters through plane A and leaves through plane D. Catalyst is coated between planes B and C, which are at a distance of 0.5 and 0.75 L from the inlet. Reactor is preheated through the top and bottom walls over the distance between planes A and B. So heat top and bottom walls are used to preheat the reactants. And we are imposing constant wall heat flux as well. So gas temperature will increase linearly. So option 2 is the right answer. So only option 2 is the right answer. So answer is option B. So now moving on to question 4, we have in figure, if the reaction rate is very high, the methane species will get consumed as quickly as it reaches the surface. In this case, the boundary condition for the concentration of methane species at the bottom wall of the reactor between planes B and C is dash. First one, concentration is equal to 0. Second one, concentration gradient is equal to 0. Third one, concentration gradient equal to constant. So in the figures, if the reaction rate is very high, methane species will get consumed quickly as it reaches the surface. In this case, boundary condition for the concentration of methane species at the bottom wall of the reactor between planes B and C is dash. So we all saw that between planes B and C, the wall is coated with the bottom wall is coated with the catalyst. And it is also mentioned that if the reaction rate is very high, methane species will get consumed quickly. Once it reaches the surface, reaction rate is very high, so methane conversion is very fast and it is getting consumed very quickly as it reaches the surface of the catalyst. In this case, what would be the boundary condition for the methane species at the bottom wall of the reactor between planes B and C? At the bottom wall of the reactor, if the catalyst is converting the reactant species very fast because of the high reaction rate, methane will not be reaching. So concentration of methane at the bottom wall of the reactor between planes B and C will be 0 actually. So option 1, concentration is 0 is the right answer. Concentration gradient equal to 0 means that there is no variation of methane across the bottom wall. However, because it is mentioned reaction rate is very high and methane species will get consumed quickly, we are going with first one, that is concentration is 0. So concentration gradient equal to constant again means it is like some gradient is constant but there is no change, like there is some gradient or the change is very gradual. In the second one, it means that there is no change. In the third one, it means that the change is very gradual with some factor. So answer is actually first one, concentration is equal to 0. So option A 1, option B 2, option C 3, option D boundary condition is not required. So answer is option A 1. because it is mentioned that the reaction rate is very high and methane species will get consumed as quickly as it reaches the surface. So because of this statement, what happens is that concentration of methane at the bottom of the reactor between the planes B and C will be zero because it is consumed as quickly as it reaches the surface due to the high reaction rate, very high reaction rate. So one is the right answer. Now we will go to question 5. Which of the conservation equation can be neglected in formulating the problem? I repeat the question. Which of the following, which of the conservation equations can be neglected in formulating the problem? So first one, it is momentum conservation equation. Second one, energy conservation equation. And third one, it is mass conservation equation. And fourth one, it is none of the above. So what is asked in the question? In the question, it is asked that which of the conservation equation can be neglected in formulating the problem? So when we are formulating any problem, which conservation equation can be neglected out? First one, momentum conservation. If we are not using, if we are not getting the momentum conservation equations, we do not know the flow velocity or flow parameters at all. So we cannot ignore or we cannot neglect the momentum conservation equation. Second one, energy conservation equation. In this particular question, in this particular case, the energy conservation is playing a major role because we are supplying external heat. Whenever heat transfer is involved, we need to solve for the energy conservation equation as well. So we cannot neglect energy conservation equation as well. Third one, mass conservation equation. Again, we cannot neglect. We need to know the species balance. Chemical reaction is happening and we need to know the mass transfer things happening inside the system, and therefore we cannot neglect mass conservation equation as well. So we cannot neglect any of the three given above. So the right answer is option D is the right answer. Option D, none of the above. Option D, none of the above is the right answer. Now we will go to question 6. In question 6, the viscous dissipation term that appears in energy conservation equation is absent in dash. The viscous dissipation term that appears in energy conservation equation is absent in dash. Option A, inviscid flows. Option B, incompressible flows. Option D, non-Newtonian flows. Option D, compressible flows. So coming back, like I already mentioned when we were writing the energy conservation equation, that 5V term, that is viscous dissipation term, is often neglected in the heat transfer problems. So the question is that viscous dissipation term that appears in energy conservation equation is absent in dash. Option A, inviscid flows. Option B, incompressible flows. Option C, non-Newtonian flows. Option D, compressible flows. So inviscid flow is that it is a simplification or idealization of the fluid flows, wherein like viscosity effects are not considered at all, and incompressible flows where density doesn't change, and non-Newtonian flows is that fluid doesn't obey Newton's law of viscosity, and compressible flows, like shear stress is not directly proportional to the shear rate, and viscosity is varying, that is non-Newtonian flows. And compressible flows is that where density is changing, and when do we neglect or when do we not include the viscous dissipation terms in the energy conservation equation? So the answer is actually inviscid flows. Option A is the answer. Why? Because inviscid flow where viscous shear and normal stresses are negligible. So in real heat transfer problems, heat fluxes are strong and temperature variation associated with the contributions are no. In real heat transfer problems, where heat fluxes will be strong and there will be a strong variation of the temperature associated with the flow conditions. And in those cases, the contribution of viscous dissipation energy will be very small. So we are mostly in real heat transfer problems, the term is neglected. And but when the flow is with highly viscous fluid flow like glycerol, crude oil, those things, viscous dissipation term is considered, work done by viscous forces. So here what is meant is that viscous dissipation term that appears in the energy conservation equation, we all know that. But in certain cases we are neglecting the effects of viscous dissipation term. One such case is the inviscid flows. In inviscid flows, the viscous shear and normal stresses are negligible. So we are also neglecting the viscous dissipation effects that is arising in those cases. Also in real heat transfer problems where heat fluxes are very strong and temperature variation is associated with the flow conditions, that is during the flow the contribution of viscous dissipation is small and we are neglecting. But when we are dealing with certain fluids like crude oil, petroleum, the viscous dissipation energy is considered. So that is the case. So coming to question 6 answer, I mean it is that rho Cp dt dou T by dou T plus rho Cp delta dot del dot U into T equal to K into del square T plus mu into phi V. So here it is that rate of change of temperature with respect to time and rate of change of temperature with respect to the convective moment, and it is due to the diffusion and it is the viscous dissipation term. Mixing of highly viscous fluids like using an impeller, the viscosity, for example, when we are mixing a highly viscous fluid using an impeller, the viscosity effects will be very high, and because of that the viscosity would generate a sufficient amount of local dissipation and local increase in temperature, which may have a consequent large change in viscosity, which would then be coming into momentum equation and that could change the velocity field. So what we are trying to say is that in inviscid flow systems we are neglecting the viscous dissipation rate term, that is over. So what happens when we are considering the viscosity, when we are considering the highly viscous systems? When we are considering highly viscous system, for example, consider the case wherein we are mixing a highly viscous fluid using an impeller. The viscosity alone would generate a local dissipation and a local increase in the temperature, and because of that velocity will change, and that change in velocity would again influence the momentum equations. So we cannot neglect the phi v term when we are dealing with a highly viscous fluid. For light viscosity fluids, viscosity term could be neglected. So highly viscous fluids we cannot neglect, but for light viscosity fluids, viscosity term could be neglected. Viscous dissipation term could be neglected. That is what the conclusion is. So now we will go to question 7. Okay. Now the time is 4 pi. I'll take a 2 minutes break and we'll resume the session in 2 minutes. Okay, we'll start now. Which of the following is already included in the energy equation that we solve along with the Navier-Stokes equations for flow with flows with heat transfer and therefore do not require further modeling? Which of the following is already included in the energy equation that we solve along with the Navier-Stokes equations for flows with heat transfer and therefore do not require further modeling? First one, it is conductive heat transfer. Second one, it is convective heat transfer. Third one, it is radiative heat transfer. So which of the following is already included in the energy equation that we solve along with the Navier-Stokes equations for flows with heat transfer and therefore do not require further modeling? So first is conductive heat transfer and convective heat transfer. Third one is radiative heat transfer. So if we go and look back at the energy equation, rho Cp dou T by dou T plus rho Cp, once again, rho Cp into dou T by dou T plus rho Cp into del dot U into T equal to K into del square T plus mu into phi V. So here this term is the rate of change of temperature with respect to time, and as I mentioned, this is due to the convective heat transfer, that is due to the flow. What is the change in heat transfer, and this is the heat transfer due to conduction. So here K is appearing. K is nothing but conductivity. So K into del square T plus mu into phi V. Here it is a viscous dissipation term. So it is diffusion term, and if we generally look at the equations, right, momentum conservation or energy conservation, we all have one thing in common. We can find the diffusive thing and rate of change with respect to time and due to the convective motion. So all these things will be there. But for coming back to the energy transfer equation, rho Cp into dou T by dou T plus rho Cp into del dot Ut equal to K into del square T plus mu into phi V. So here we have convective heat transfer, that is this term, and this is conductive heat transfer though. So we have included conductive and conductive terms in the energy equation itself. This equation is what we solve along with the Navier-Stokes equation. So coming back, which of the following is already included in the energy equation that we solve along with the Navier-Stokes equations for flows with heat transfer and therefore do not require further modeling? So option 1 conductive heat transfer and option 2 convective heat transfer. So both are true, whereas radiative heat transfer we haven't included. If we need to model separately. So option A 1 only, option B 1 and 2, option C 1, 2 and 3, option D none of the 3. So answer is option B 1 and 2 is the right answer. Option B 1 and 2 is the right answer. So now moving on to question 8. Okay, question 7. Advective term includes velocity and takes care of the convective heat transfer. Constant property form for the energy conservation equation. Rho Cp, constant property form wherein Cp, that is specific heat capacity, density, so we have just constant property, and this is the energy conservation equation. So advective term includes the velocity and therefore takes care of the convective heat transfer, and this term takes the conductive heat transfer. Alright, now moving on to question 8. Now in this question we have well-posedness of an initial value problem means dash. Option 1 having guarantee of a solution. Option 2 having guarantee of a unique solution. Option 3 having guarantee of a solution that is commensurately responsive to changes in initial and boundary condition. So what does well-posedness in an initial value problem mean? So we are given 3 statements. First we will go through each of the statements and identify which of them are right. So here it is an initial value problem and we are asked to define the well-posedness of an initial value problem and what does it mean. So the first one is that having guarantee of a solution. True. When we are dealing with the initial value problem, when we have the guarantee that there is a solution, we call it, that is one criteria. And second one, it is having guarantee of a unique solution. Again, this is true because that solution should be a unique solution. So normally, if there are multiple solutions, right, that it won't be a properly defined problem statement. We would have missed out something, or something else is missing, or something is given over information, something like that. So those things also come into picture. So having guarantee of a unique solution is true. And third one, having guarantee of a solution that is commensurately responsive to changes in initial and boundary conditions. Again, third statement is true because we need a guarantee that it is responding very well when we change the initial conditions and the boundary conditions. It should not be fixed for that specific initial or boundary conditions. So it should not be that case. So well posedness of an initial value problem mean that having guarantee of a solution, and that solution should be unique, and that solution should also respond to changes in the initial and the boundary conditions. So three statements are given and all of them are true. So based on that, if we look at the options, option A 1, option B 2, option C 1 and 2, option D 1, 2 and 3. So since all three of them are right in our estimation, we are going with option D 1, 2 and 3. So option D is the right answer because well posedness of an initial value problem means having a guarantee of a solution and guarantee of a simple solution and guarantee of a solution that is responsive to changes in initial and boundary conditions. So now coming to question 9. In homogeneous chemical reactions, all the reactants are in the same phase. In heterogeneous reactions, at least one of the reactant species is in a different phase. Which of the following statements are necessarily true? Option 1, statement 1, all catalytic reactions are heterogeneous. Second one, all electrochemical reactions are heterogeneous. Third one, all reactions involving gaseous reactants are homogeneous. I think all are wrong, I guess. Options, we will look at the options once. Option A 1 and 2 only. Option B 1 and 3 only. Option C 2 and 3 only. Option D none of the three. So what does it mean is that in a homogeneous problem, we have like chemical reactions, we can call it two ways. One is homogeneous, one is heterogeneous. When do we call a reaction as homogeneous? When the reaction is when all the reactants are in the same phase, we call that as a homogeneous chemical reaction. And if all the reactants are in a at least one of the reactants are is in a different phase, we call it a heterogeneous reaction. So I repeat again, homogeneous reactions, we have all the reactants in the same phase, and in heterogeneous reactions at least one reactant would be different phase. So depending on the phases, we can call it as a homogeneous or heterogeneous reactions. So based on that, what are all the statements that are true? First one, all catalytic reactions are heterogeneous, that is false. Second one, all electrochemical reactions which involve ionic species are heterogeneous. Again, it is false. We cannot generalize the statements. There are cases where it is opposite. And third one, all reactions involving gaseous reactants are homogeneous. Again, this is false, like because in not all the time all the reactions involving gaseous reactants are in the homogeneous. There are heterogeneous reactions as well. So all three statements are basically false. So coming to the options, option A 1 and 2 false, option B 1 and 3 false, option C 2 and 3 again it is false, option D none of the three. So answer is option D, none of the three is the right answer. Option D, none of the three is the right answer. Now we'll go to question 10. In question 10, it is asked that diffusivity of a gas species depends on which of the following? Diffusivity of gas species depends on which of the following? So diffusivity is nothing but the rate at which that particular gas molecule, gas species can move through the mixture. So we'll see the options. First one, temperature. Second one, pressure. Third one, concentration. So diffusivity of a gas species depends on which of the following. So three options are given. First one, temperature. Second one, pressure. And third one, concentration. So actually diffusivity of a gas species depends on all three. Option A, 1 only. Option B, 1 and 2. Option C, all three. Option D, independent of all three. So actually answer is option C, that is all three. So diffusivity of a gas species depends on which of the following: temperature, pressure and concentration. So it depends on all three. How is that? Diffusivity is a measure of how quickly a substance can move through the another one due to the concentration gradient. So because of the difference in the concentration gradient only, it moves. And like when the temperature is like high, it affects the diffusivity because the kinetic energy of the molecule will be affected, and therefore the more kinetic energy and increased diffusivity, those things will be there. And also pressure, if pressure is high, it decreases the diffusivity because there's less space to move. And gas composition, again concentration, like how much the concentration is, based on that concentration gradient only it generally moves. So diffusion is in a gas molecule, diffusion of a gas species depends on the temperature, pressure and concentration, all three. So option C is the right answer. Option C, all three is the right answer. So now we will go to question 11. In question 11, what is asked is that which of the following is a typical fluid flow boundary condition? So there are few boundary conditions given and we need to identify which of the following is a typically used fluid flow boundary condition. First one, it is uniform velocity at inlet. Second one, uniform velocity at outlet. Third one, zero shear stress at wall. So answer is option 1, that is uniform velocity at inlet is the right answer. We look at the options anyway once. Option A, 1 only. Option B, 2 only. Option C, 1 and 2. And option D, it is 1 and 3. Option A is the right answer, because in the question it is asked that which is a typical fluid flow boundary condition. So consider a flow through a pipe. What can we specify about that flow through the pipe? We can know that velocity at the inlet, because we are passing the fluid inside the pipe. We know the rate at which it is entering, and we also know the velocity at the inlet condition. So uniform velocity at the inlet, it is one of the typical fluid flow boundary condition. And second one, uniform velocity at the outlet. At the outlet, we do not know what condition it is coming out. So we cannot comment on how velocity at the outlet is. So uniform velocity at outlet is the wrong answer, because we do not know the outlet velocity in most cases. Inlet velocity we know because we are passing the fluid inside that system at that particular velocity, whereas the fluid coming out of the system is being affected by the flow that is happening inside the system. For example, pipe flow itself, if we consider, we are passing the uh, fluid. Like for example, consider a pipe of length 1 meter and we are passing the fluid inside the pipe at velocity of 0.1 meter per second or something. We know that approximately after 10 seconds it will come out, and but because of any flow disturbances that is happening inside the system, that is inside the circular pipe, we do not know the outlet velocity, so we cannot comment on the uniform velocity outlet. If we give, that will lead to wrong results. And third one is zero shear stress at the wall. So again, like zero shear stress at the wall, it is like we cannot say that it is not a typical fluid flow boundary condition as well. Generally, in normal cases, in fluid flow through a pipe itself, if we consider what boundary conditions we specify is that in the inlet it would be mostly pressure velocity inlet, and in the outlet it would be pressure outlet. Like because of that, it will calculate automatically, and at the walls it would be no slip boundary condition. What does no slip boundary condition mean? That it means that the velocity at the near the wall is zero at the solid surface, or if wall is moving, it will be equal to the velocity of the wall. So if the wall is stationary, the velocity at the wall will be zero, but basically velocity of the fluid at the wall is equal to velocity of the solid, that velocity of the wall surface. It assumes that the fluid layer in direct contact with the boundary has the same velocity as the boundary. So the statement will be clear. No slip condition, that is which what we typically apply at the boundary layer, that is at the wall, assumes that the fluid layer in the direct contact with the boundary has the same velocity as the boundary. So like that is the normal boundary condition which we apply at the wall. Next is the pressure outlet boundary condition. So this is normally we use in combination with the inlet velocity. So it is used like mostly it will be like open to atmosphere. So those type of things we know, right? Outlet, it is open to atmosphere. So pressure at the outlet, we can give it as atmosphere pressure. So those things, it we need to specify it in such a way, but we cannot say that velocity value, we cannot specify the velocity value at the outlet. Uniform velocity at outlet we cannot specify. Maybe like some other conditions in terms of gradients we can give, but not a uniform value. So option question 11, the right answer is that uniform velocity at the inlet is the right answer. That is option A, one only is the right answer. Our answer is option A, one only. Now we'll go to question 12. In question 12, it is mentioned, it is asked that Navier-Stokes equations are all partial differential equations. What will be the best reason behind this? So we are using Navier-Stokes equations everywhere for solving fluid flow in the particular system. So why Navier-Stokes equation is a partial differential equation, and what is the reason behind that? So that is a question. We'll see the options. Option 1, ordinary differentials are not present in the Navier-Stokes equation. Option 2, dependent variables are functions of all the independent variables. Each dependent variable depends on only one of the independent variables. Partial differentials are not are only present in the Navier-Stokes equations. So what we have is that Navier-Stokes equations, we all know it is a partial differential equations, and we also know that that is like why it is like difficult to solve it also, and why we call Navier-Stokes equation is as a partial differential equation. First one, it is differential equations are not present in the ordinary differentials are not present in the Navier-Stokes equations. And second one, dependent variables are functions of all the independent variables. And third one, each dependent variable depends on only one of the independent variable. And last, partial differential equations are present in the are only present in the Navier-Stokes equations. The right answer is that it is option B is the right answer. Because dependent variables are functions of all independent variables. Like it is considered because the motion of the fluid by relating the velocity change with respect to not only time but also with spatial coordinates like x, y, z. It involves derivatives with multiple variables simultaneously. Like it is changing in time, it is changing in x direction, y direction, z direction. So that is why we call it as a partial differential equations. Dependent variables are functions of all the independent variables because the equation considered how velocity changes with respect to both time and positions in the three-dimensional spaces. So we are taking the partial differential equations, derivatives, derivatives to be taken with all the variables, that is x, y, z and time. So option B is the right answer. Dependent variables are functions of all of the independent variables. Now we'll go to question 13. In question 13 it is mentioned that Navier-Stokes equations are dash system of equations. Navier-Stokes equations are dash system of equations. Option A, coupled. Option B, uncoupled equation. Option C, exponential equation. Option D, radical. So actually we call Navier-Stokes equations as a coupled equation and it falls under the coupled system of equations. So option A is the right answer. So why? Because it is like pressure and velocity term are both like appearing together, so we cannot split those while solving the equations. So that is the reason it is like very difficult to solve Navier-Stokes equations. In general, yes, it is difficult to solve Navier-Stokes equations because of the because it is a coupled system of equations, because the varying terms appear together in the equations. We cannot separate it and solve them separately. We need to solve those system of equations together simultaneously, so that is becoming a complex in getting the solutions. All these things you will see when you study. These concepts will become much clear when solution to Navier-Stokes equations come in the future classes. But just to give you an idea, I have included the question. So answer is option A, that is coupled system of equations. Now we'll go to question 14. In question 14, we'll see what is asked. The physical principle behind the energy equation is dash. The physical principle behind the energy equation is dash. So few questions are more. It is not a very more. It is just a basic questions. So related to energy equations, momentum equations, and species balance equations. So those are all the questions that are coming up. Like serious, more problem oriented questions we have seen till now. So these are just to refresh your basic concepts. Those things only I have included. So Question 14. Physical principle behind the energy equation is dash. Option A, Newton's second law of motion. Option B, zeroth law of thermodynamics. Option C, first law of thermodynamics. Option D, Newton's first law of motion. So, physical principle behind the energy equation is dash. So, options given are Newton's second law of motion, Newton's zeroth law of thermodynamics, first law of thermodynamics, and Newton's first law of motion. Whenever we say energy equation, what we mean is that it is an energy conservation equation. That is, energy is like neither created, it is, zero, sorry. First law of thermodynamics states that energy cannot be created or destroyed. It can only be changed from one form to another. So that basically is the energy conservation equation. So similar thing is what we are doing in our energy equation as well. We are just giving energy into the system, and because of that there is like utilization of that energy or production of new energy or consumption of energy, whatever it is, so that we are calculating. So rate of change of temperature with respect to time plus rate of change due to the convective motion equal to the rate of change due to the diffusion plus due to the conductive heat transfer. That is what is given in the energy conservation equation. So it basically states the first law of thermodynamics only. That is, energy is conserved in the system. It is like, so option C is the right answer. Option C, first law of thermodynamics. The physical principle behind the energy equation is first law of thermodynamics. So coming to question 15, we have that source term in the momentum equation is dash. Option A, pressure force. Option B, body force. Option C, viscous force. Option D, acceleration. So we have momentum conservation equation. In that actually we have 4 terms if we simplify the equation. So it is that, if you want I can show the equation as well. So it is a momentum conservation equation. Dou u by dou t plus del dot u into u equal to nu into del dot del u plus g minus 1 by rho into delta p. So this is the rate of change of momentum with respect to time and rate of change with respect to the convective motion, and this is due to the diffusional effects, and this is the body force, and this is the pressure gradient force. So all these things if we see, it is like a surface forces except the gravitational force effects, gravity effects. So it is coming from the body force. So it is the additional thing. So it is the source term that is, so it is a source term that is giving us those things. Source term in the physical, in the momentum equation is dash. So it is body forces. Option D, body forces is the right answer. Effect of surface forces are external. They are not produced inside the body. Body forces are created inside the body of conservation. So the body force is the source term. So like effect of surface forces is external, whereas they are not produced inside the body. So what we mean by source term in any equation is that something is getting generated in the system or like inside the body of conservation. So here surface forces are effects are external, but whereas the body forces is like generating inside the, created inside the body of conservation. So body force term is the source term. So it is body force is the source term. So now moving on to 16th question. We have under specification of boundary condition gives rise to dash. Under specification of boundary condition gives rise to dash. We'll see the options. Option A, solution equal to 0. Option B, no solution. Option C, unique solution. Option D, n number of solutions. So what is happening? We are giving boundary conditions in the systems. If we are under specifying the boundary condition than that is required, what will happen? So it is similar to how we deal with degree of freedom, those problems. It needs to be, if we need to know, like we are just using the boundary condition to solve the equations, right? What if we under specify the boundary conditions? It is like we are giving a less number of values than that is required. So answer is like we will get n number of solutions. So under specification of boundary condition gives rise to n number of solutions, because we are giving values less than what is required. So the possibility of having so many solutions are arising in that case. Like if we give one less boundary conditions, that value we can take it as anything. So if it is not specified, that value can be any value. So the solution also will be varying in that high fashion, like n number of solutions we will be getting. Under specification of boundary conditions gives rise to n number of solution. Option D is the right answer. And yeah, answer is option D, that is n number of solutions. Under specification of boundary conditions gives rise to n number of solutions. So option D is the right answer. So now we will go to question 17. So this is the last question for today's session. What happens with the overspecification of boundary conditions? Option A, infinite solutions. Option B, unique solutions. Option C, unphysical solutions. Option D, no solution. So what happens with the overspecification of boundary condition? So if we are specifying the boundary condition more than that is required, what happens? So previous case, what we have seen is the under specification of boundary conditions. So in that case, we have seen that if the boundary condition is specified less than that required, it will give rise to n number of solutions, because that particular value can be anything. So the solution can also be anything. Like there is no finite number of solutions that we should be getting. What ideally we should get is that the boundary condition should be specified in a correct manner, so that those calculations will, so that it will be used in the calculations, and we will be getting a single unique solution. That is what is our ultimate requirement, right? We need to get a single unique solution, so that is accurately predicting the dynamics happening inside the system. Whereas if we are under specifying it, we are giving, or we are opening the way to getting a n number of solutions. Similarly, this question asks what happens when we are over specifying the boundary conditions. So imagine that you are heating a system, okay, and you are placing a heating rod at one end of the solution. So you are giving heat to that end, and another end can be insulated end. So there is only one possibility of getting the solution. For example, we are having one rod where we are giving some T Kelvin over here, and if it is insulated rod, okay, you are understanding, right? It is insulated. So what happens is that here we know it is temperature is this particular temperature, and here it is insulated. So there is no heat escaping the system, so we can give as heat flux is 0, because there is no heat exchange with the outside because of the insulated boundary condition. And here we can specify temperature as T is equal to 100 degrees Celsius, something like that we can give. But these are the unique or exact specification of the boundary condition. But over specifying it, we cannot give two boundary conditions over here, right? We cannot give as temperature is equal to 100 degrees Celsius, and at the same time we cannot give it as temperature is equal to insulated walls, or temperature is something else. So those type of things we cannot actually do, because if we do, what happens, it will give some unphysical solutions. First of all, it won't be exactly possible to choose that. Imagine it cannot go ahead with two boundary conditions, right? Over specification of boundary condition is therefore not possible first when we are using commercial solvers. But if you are defining your case and if it is going ahead with that, it will for sure lead to unphysical solutions. It will not give a proper solutions. You can imagine now, right? We cannot give more number of boundary conditions than that is required. Similarly, in the previous case, what was happening, we are under specifying the boundary conditions. What happened that time, we are giving temperature over here as some 100 degrees Celsius, but here we haven't defined the boundary condition. So what can happen here, it can be insulated wall, or again another heat source can be placed over here, we do not know. So it can lead to n number of solutions. Again, that is not practically feasible, because it will throw error when you are using a commercial solver. And this case is also practically not feasible when you are using the commercial solvers, because it requires what how much ever is required, that much only. But with the under specification, it will lead to a number of solutions. And similarly, with over specification of the boundary conditions, we know that it will lead to unphysical solutions. The solutions would not be practically feasible, and its solutions we can't even imagine. So that type of solutions we will be getting. So answer is option C is the right answer, unphysical solutions. So yeah, that's all for this week. Thank you. If you have any questions, you can ask now. Similarly, like, we'll meet next week from same time 3 p.m. to 5 p.m. and we'll discuss next week's problems. So these lectures and notes are also available. You can use it for your later purposes if anytime it is required. So yeah, if that's all for today's class. If you have any feedback or if you have any questions, you can tell. Oh, okay. Actually, sorry, I didn't say check your answer at that time. I am really sorry for that. Anyway, thank you. Okay, if there are any doubts, if there are no more doubts, I'll close the session. I'll also stop the recording. You can use the recording for future also. Thank you. Thank you for attending.